Hey guys, thank you for joining Your Technology Coach. My name's Steve, your STEM educator and host for this channel. Hey, I'm so super excited today. This week in the mail, I've got a new STEM kit. This STEM kit is from the Snaptricity circuit line. It is available for STEM educators, homeschoolers, public schools, and I'm going to talk to you about that later, and I'm going to provide a link in the description below. So if you're new to this channel, please hit the like, subscribe button, and let's talk about this product. All right, so this is a Snaptricity set that just, I think it was released a little bit ago, but the aerospace education program I'm a part of just got a hold of it. And I want to go through some of the new components that are part of this program now. So a lot of times we've had just the basic components. We've had speakers, we've had microphones, all those kind of things. With this one, we have an actual electromagnetic device here that we can use for other applications, which I'll show you later. We have our basic motor. We've used those in projects before. This one here is new. With the electromagnetic component of this, and also the filings, the iron filings that we have, we also have a compass. And a regular magnet, double pole on this. And you can notice that obviously it is going to impact our compass magnetically. We have different switches this time that we'll be using, and we have a push button switch along with the basic propeller type fin fan system there. And we have another bag of other components that came with the program. There's some paper clips in here, some rope. There's a plunger type metal device that goes into the electromagnet. And there are a ton of programs and really easy to follow examples in here of what we're going to do. So this makes it really easy for someone who, a teacher who's not done electronics before or has not worked with this, but it just provides a whole realm of experiments. So there's really no limit where a STEM kit like this can take you. So enough about that. I'm going to take you on some projects here, and we're going to do two to start out with. We're going to look at basic circuits and show you how those work. Oh, by the way, the one thing I do like about this program, this new kit, is that it's got an ammeter built into it, or actually you can put this in different places. This is going to be very helpful when we're trying to read measurements on amperes and volts. However, though, I always recommend having a basic voltmeter or a multimeter as well if you want to check resistance, if you want to check little different voltages and those kind of things, both with the direct current and alternating current. Anyway, let's get into our project. Okay guys, so for this lesson, we're gonna go through a basic series circuit. Now, if you watched my earlier videos, we talked about what a series circuit is, what it means, and how it operates. So if you think about former like Christmas lights back in the day, or lights that were all connected to one outlet or one source of electricity, when the source of the power would go out, they would all go out. So similar circumstance, we have our load, or I'm sorry, not our load, but our source, which is our battery pack. This is a 4.5 volt battery pack. And we know that because each AA battery is 1.5 volts, and we have 3 of them in place. So adding them all together gives us 4.5 volts of electricity. With this kit, there is like I said, an ammeter, which also shows you volts, but I also have my own little multimeter as well. That way we can make sure that, we're getting the right voltages and we can see exactly what's going on. So for this project, it is project number 20 in this book, and it tells us very easily, very simply, and very plainly where things go on the grid. The grid is very easy to understand. So when we put things in place, we know exactly where they're going. It tells us in the assembly portion where to start, what to do. We have an operations portion, which tells us how we go about once it's built, what we're going to be doing, and exactly what functions are going to occur. We have the description, basically telling us what we can do differently or what we're going to be doing as far as experimenting. So in this project, we're going to be doing a series swap, which means we're going to be taking the amp meter and positioning it in different places throughout the circuit and seeing what the results are. And then at the bottom is our education corner. This goes through a full detail, but it's pretty plain as far as someone who doesn't have electronics background can easily understand this and apply it to a lesson. So this whole page right here could be one lesson in your full scope of curriculum for an entire year or half a year. So what I've done is I followed the exact plan as how they have it laid out on our drawing. I set it up exactly on the grid that we have. So I have my battery pack, I have my conductors or conduits, and I have three incandescent light bulbs. All right. Again, this is a series. So when I flip the switch, the electrons are moving one direction around the series, kind of like a racetrack. All right. This will be different later when we talk about a parallel circuit. So I'm going to flip the switch on this, and you can see on screen that the lights came on. However, they look really dim. And the reason for that is that the 4.5 battery pack has to provide enough amperage through all the lights. So if you notice, you may not be able to see it on the screen too well, but this light's a little brighter than the other two. Okay, if you notice also, our ammeter has moved up a bit. So I'm going to just kind of turn this off so you can see it, the activity on there. It's off. And now it's on. So you can see on the ammeter that we're right about running less than maybe just a few, maybe 0.5 milliamps on there. And we're running maybe around 1.5 to 2 volts on the bottom screen. Now I can confirm that by using my regular multimeter and putting my, backwards here, I want to do it. It doesn't really matter because we'll, on this part, since we're DC electric, we're just going to put the components here like this. Oops, I'm sorry, I want to go this way here. And I'm running about 1.5 volts. You may not be able to see it perfectly. I'll put that on the screen there. So there we go. We're running just, there we go. Yeah, around 1.56. If I come down here, I'm getting 3.06. And that's volts. All right. So I'm going to take this out of place. Now, again, anytime I make a change, I want to make sure I turn off the electric first. All right, so everything's off. And what change I'm going to make is I'm going to take a cross connector here, and I'm going to remove the 2 additional incandescent lamps. So I'm going to put this across here. So essentially, I've created a short circuit. So electricity, as we know, follows the path of least resistance. Electrons don't like resistance. They want to flow, they want to move, they want to do their thing. So I've now created a short. Now, if I wanted to be safer about this, I'm just going to remove one component. That way I don't have an accidental cross of electricity, okay? Not that it means much, but it gives me a peace of mind. All right, I'm going to turn on the power now. And whoa, that is really bright. So again, being in a series circuit, I've removed the other loads or the other resistors from the circuit, which now dedicates all the power from the battery pack, from the source, to one incandescent lamp. Now, if I was to take my voltmeter again, or my multimeter, and I was to look at that, okay, so I'm going to put that up there. You're going to see, again, if I measure the battery pack itself, I've got right at 4.5 volts, which is almost the entire amount of volts and current going through here. So if I measure it right to here, I have almost exactly what's coming out of that pack because I have no other resistors before this lamp. Okay, so we're going to move right across the page to project number 21. Project number 21 talks about parallel circuits. So we went from series, which was everything in one complete loop, to a parallel circuit. Parallel circuits are very similar to the lights in your house. When you turn on a switch, for example, your kitchen, only the kitchen lights will turn on. If you turn the switch off in a bedroom, only the bedroom lights will go off, not the entire house, or not the kitchen and a bathroom and a bedroom. So parallel circuits are very important, especially for households and places where you only have a certain area where you want to supply or not supply electricity. So in this case, this is our parallel circuit. We have our same 4.5 volt battery pack, but we've removed some items. I removed the ammeter because we're going to use our basic multimeter. We have our switch and we have 2 incandescent lamps. So when I flip the switch on the project, notice that both lamps come on about the same strength. Pretty much they are at the same strength. So if I take my voltmeter, set that up, and I'm going to measure across the first lamp, and I'm going to get roughly 3.93 volts. Measure across the second lamp, almost the same. So roughly 3.9 volts on both, because in a parallel circuit, the electricity, the amperage, is spread across a bridge equally to both loads or both devices, whether it's a lamp, whether it's a motor, a fan, or whatever it has to be. In a series circuit, the amperage is being diminished or shared as more devices in the loop are being energized. Now, the downfall with this is, the more devices I put in parallel is the more that the battery pack is under stress or duress and is providing additional power. So my chances of my battery pack depleting quicker is a lot greater. So I'm going to turn this one off, and I'm going to add in another incandescent lamp. So I'm going to take this one out of the mix, put this one in. That's Snap Circuit. You just heard it, the snap in the circuit. That's why I like these so much. So, hey, by the way, while you're watching this, don't forget in the descriptions area below, I'm going to put links to resources for what I'm using in this channel. So also make sure you hit like and subscribe so you're aware of the new stuff that's coming up shortly. So I'm going to turn this back on and let's see what happens. Okay, look at that. What do we think happened here? Interesting, huh? So right now I've only got one light turning on. Make sure everything's set. And it looks like this light is taking all the power from the other ones. These are very, very dim. You can barely see that those lamps are energized at all. So if I measure, let me get this out of the way here, what's going on in this circuit, I've got 3.45 volts. Let's see what's going across this circuit. Wow, look at that, 0.79 and 0.79. So this load here, technically it's from a series to a parallel. This is taking a lot of the load away from these devices. So this would not be an efficient circuit that I would use in an environment like a house or a building or some kind of project like that. All right, so this is why I was really excited about this product. So on page 55, project number 46, it talks about electromagnets. Now, when you think about electromagnets, they are everywhere and you don't really notice it. They're in cars, they are in refrigerators, they're in appliances, things you use every day and don't even know it. And the principle of electromagnetic force is that when power is energized to an electromagnet, it turns on. When it's de-energized, it turns off. So when I look at this device by itself, I notice there's a lot of cable in there. There's a lot of wire. So when I wrap wire in a cylinder format, I'm going to say that really quick, a cylindrical format, okay, there's some geometry for you. I increase the amount of electromagnetic force that the magnet is able to produce. So in this sense, every wire, every wrap around the cylinder is increasing the electromagnetic force of this magnet. So when I energize it, it then will create a magnetic pole to attract other metals, specifically something with iron in it, to itself. So here's how this is going to work. So I've placed a core or a metal core through the electromagnet, which is going to act as my little pole here to pick things up. So as I'm working with this, you notice nothing's really happening. Not doing anything fantastic right now. I'm just pushing these things around. All right. But when I energize this, I'm going to turn this on, and you don't see anything, you don't feel anything, you don't hear anything. But when I now attract this to something metal, the magnet is energized because the electrons running in circles around that core hundreds and hundreds of times are creating an electromagnetic force. Now, when I turn those electrons off by closing or opening the switch, isn't that cool? Isn't that cool? So I'm going to turn it on again and watch what happens. So I'm going to try to tap this nail. Nothing's happening until I turn the switch on. Look at that. Now I'm going to turn the switch off. The electrons stop. The magnet is de-energized. Now let's see if I can pick this little wrench up here. It's a little heavier than everything else here, but I think it's going to be able to do it. So here we go. Turn on the power. Magnet is energized. Look at that. Oh, I got it. Now, magnets are as powerful as the amount of electrons running through them. So given that I'm only running 4.5 volts from my battery pack, if I was to increase that, increase the voltage and the power, as well as the amount of times I've circled the core in there with additional wire, I would strengthen the electromagnet, and it would pick up a lot heavier things. See, it was just barely picking that up. So I'm going to turn this off. Now, one other thing where electromagnetics come into play is the Earth itself is a giant electromagnet. There are two poles to the Earth. You have a North Pole and a South Pole. Those are always giving off electromagnetic force. So when you think of a compass, all right, a compass is designed to point to magnetic north. So no matter where I turn the magnet, or the compass, it should be pointing to a magnetic north, which in this case is that direction, okay? So think about avionics, think about airplanes, think about GPS systems. When you're traveling, compasses and electromagnets are very, very important, because if electromagnetic energy interferes with the radar systems or compasses of an airplane, then you could be going to a totally different destination. When you think about if you've ever flown in a plane, and one of the things they tell you is to turn off your electrical devices. Well, the reason they do that is because that many electrical devices at one time in a plane can very significantly mess or create inaccuracies with the compass abilities in the aircraft. Watch what happens where right now my compass is pointing north. All right, north is that way. All right, I'm actually pointing, the direction of this video is pointing east, west is behind me, and south is that way. So I am pointing magnetic north. I'm going to place the electromagnet right in this position. I'm going to turn on the magnet. I'm sorry, yes, here we go. Magnet's on. And watch what happens to the compass. Oh, I am interfering significantly with the ability of the compass to do its job because the electromagnetic force is pulling that needle where it shouldn't be going. But the moment I turn that off and reset the compass, let it find its way, now I'm back to magnetic north. Hey guys, well I hope you enjoyed this episode of Your Technology Coach, working through these STEM products with Snaptricity and electrical circuits. If you found this helpful, please forward it on to folks in your community, whether it's the homeschool community, public school, or universities. We'd be happy to get feedback and to work with you guys on new channel ideas. So please, we love your comments, love your feedback. So again, my name's Steve. Thank you for watching.